now the third part, which I nearly forgot about, but it's the most important one, because as I will try to convince you several times, if you want to deal with some mathematical objects, we call it category of objects, or some type of objects, say, like vector spaces, affine spaces, etc., then the most important thing is not the objects, but the morphisms. Because knowing about how the structure preserving mappings could behave and what they are is actually giving you all the tools you need, and nothing else can be just used instead of that. So this is, well, what we call affine maps. The transformations will be the affine maps, which will be bijective, right? So we touched it already when we talked about how the coordinates are changed, because of course the change of coordinates is something which preserves the structure, and therefore the change from one frame to another frame must be achieved by an affine map, which is a bijective. So what would be the affine maps? The definition at the first glance looks a little bit strange, weird, right? In vector spaces we had the linear combinations, so that was easy, so we thought, well, why not to take the maps which preserve the linear combinations, and that's it. In the affine maps we mostly just meet the following situation. So we have a mapping between the points, and we want to see that if we apply the mapping to a shifted position, so if we go from A to A plus V, so that's a change of position, then we must get some appropriate change of position of the value. And to keep the structure right, preserved, we simply want that this should be happening via some linear map. So actually we need two maps. One is the map F between the points, and the other one is a linear map between the difference spaces. And this is of course the most natural definition, although it looks a little bit weird, right? So of course the maps F and phi will be completely determined if we know the values of enough points. And what does it mean, enough? So what is a frame? That's the full analogy to the vector spaces. A frame is a point plus the linear base of the difference space. So in other words, if it's n-dimensional space, then we have got n plus 1 points. And we have to map the n plus 1 points, and then of course for the basis vectors, which are the differences from the origin from the other points, will give us the basis. And so the differences of the value will give us the values of the basis, and this defines the map phi, right? So we just map the origin in our coordinates, so having these k plus 1 points in general position, and just applying the map F, we get the phi in a unique way, and the vice versa. If we have got the phi, we just decide how to map one point, and all the rest is given by the phi. But how does it look then if we employ the concept of the affine combinations, right? So what about if we take an affine combination? Recall that means that the sum of the coefficients must be 1. Then of course, just employing the definition, you will see that you get again the very same affine combination, right? It's a very simple argumentation. Here you see, you write in what it means, right? This linear combination means exactly that you take A0 and add the differences from all the points to A0 with the remaining coefficients T1 to Ts, which might be arbitrary, right? So T0 is just the difference, 1 minus all of those. And then by the very definition here, you see that this will be nothing but the value of the point plus the action of the linear map, and the linear map is linear, so it respects the linear combinations. So it's this. But that's again the linear combination. Here you can write it down the same way as before, and that's the linear combination. So the affine combination. So you see that actually each affine map preserves the affine combinations, which we had to expect if it's right, and it also holds the other way around. So the affine maps are exactly those maps which preserve affine combinations of points. Right. Actually, if we want to check the invariance of affine combinations with respect to affine combinations, we can restrict ourselves to pairs of points, because iteratively making the affine combinations of pair of points leads us to an arbitrary affine combination, right? So because you see it here, so you can always write it as the combination of the last one with the previous ones. And therefore it's important to restrict our attention to just 2 points, and there we talk about the ratio of points on a straight line, right? So the idea is you have got a straight line, so I will draw a picture for that to see it nicely. So you have got a straight line, 2 points there, point A, point B, and then there is a point C. The C might be here, or it might be here, or it might be here, and in every case we just write down the ratio of the points C with respect to A and B, right? And that's computed in such a way that each of such points C is given as a affine combination of the 2 points. So you have 2 free parameters there, R and S, and we simply define the ratio lambda to be, well, for some technical reason it's taken with minus sign, no, I don't want that, minus S divided by R. So you see the sign is chosen in such a way that the center of the segment AB would be 1/2, right? So that's what's seen here. So C can be computed either this way or this way, both works, and you see that if R is S is 1/2, then the ratio will be just the no, I was wrong. So the center will come with -1, right? And now, of course, by the very definition, we can say that the affine maps are exactly those which respect the ratios. So that's a bit confusing claim, right? Because first of all, in order to be able to say that it respects the ratios, it must map lines to lines, right? Because we just were talking about ratios on lines. So this should be a consequence, right? Then, so take it with some reservation, but we shall come back to that when we will talk about projective maps, and then it will get more clear. Right, so the last thing to talk is then what is the coordinate expression of the map. So if we take 2 frames, in the beginning, in the end, how shall we write down the affine maps? But that's obvious, right? It must be in the matrix calculus just the value of the point A0 is Y0 in the coordinates, and then the rest is a linear map, so it's given by some matrix. So we have got 2 things to define an affine map: a matrix, and the matrix must be of the right shape, right? So it depends on the dimension of the target and the dimension of the source, and this is a vector so a point in the target, not a vector, right? So that's easy, and of course we would like to see how it changes. So if we just change the frames on the beginning, so say the original coordinates will be expressed with respect to the new ones, and then on the target we do the same, so the new ones will be expressed via the original ones. Then putting it together, we get the map in the dashed axis and written in the dashed y's. and this is what we want. And of course we just plug in, and in coordinates it's just counting with matrices and vectors, right? So you see it's just straightforward, and you see what it is. So it's quite complicated on the side of the final value, right? Because with the final value we have to count with the transitions of the origins in our coordinates. So first there is the transition W, and this will be influenced by the mapping Y itself, and then also by the change of the linear part of the frame, right? And then there is the value, which will be changed only via the change of the new coordinates, and there will be the final shift Z. So this is the change of the point in the expression for the thing, and here you see it's just what you expect at the linear side. So there is just a simple multiplication of the matrices as we know it from the vector spaces. So that's it, and that's finally really what I wanted to say for this week.